Hi all, I'm Lorenzo Steccanella and I'm happy to present our work on state representation learning for goal conditioned reinforcement learning. This is a joint work with my supervisor, Professor Anders Jones. In this work, we consider a setting of goal conditioned reinforcement learning, where an agent receives a desired goal as input. In particular, we consider a specific setting where the goal space is equal to the state space, so we want to learn a goal conditional policy that can reach any state in the state space. And moreover, we consider an offline setting where we have access to a dataset of trajectory collected by an unknown behavior policy, and these trajectory are unlabeled in the sense that they don't contain information about the goal and the rewards. Previous work tried to learn in this setting by means of using offline reinforcement learning and by relying on a self-supervised reward function and relabeling transition. The self-supervised function gives a +1 reward when we transition to the goal state and a 0 otherwise. And goal state in this setting are simply sampled as state in the dataset. This presents some issue like the state identification issue, defining this self-supervised reward in an environment where the state space is continuous or where the state space is affected by some noise is hard because we don't know how to identify whether two states are the same state. And the issue of parse reward, that simply relabeling transition by sampling random goal state uniformly from the dataset will provide an extremely sparse reward signal, making a very challenging learn in this setting. So motivated by this issue, we try to understand whether it's possible to learn goal conditional policy without having to define the self-supervised reward function. We propose to learn the minimum action distance representation. The minimum action distance is defined as the minimum number of decision steps in order to move between any pair of states in the state space. And we rely on the notion of trajectory distance to learn it. Trajectory distance is defined as the number of decision steps required to move between two states along a trajectory. In particular, here we present an example to define the trajectory distance. Here we have the trajectory T1, and we have that we want to move from S3 to S5, and the trajectory distance along the trajectory T1 for moving to S3 to S5 is going to be the number of steps that separate these two states, that is 2. So given any pair of states and given any trajectory, we know that the trajectory distance is going to be an upper bound on the true minimum action distance, and we rely on this in order to define a constraint optimization problem that help us learning this representation. Here we are interested in learning a mapping from state to RD, and we have that the objective is simply trying to say that the norm distance in the embedding space should match the trajectory distance along the dataset. So we are enforcing this by the objective, while in the constraint we are enforcing that the norm in the embedding space must be always equal or less than the trajectory distance along the dataset, and by using this constraint, we are constraining the solution to be the minimum action distance representation. Here we propose a simple example to show how this works. Like here we have a simple grid word, and we have a mapping from state to R2. And we have a simple grid word where we have an agent that has to pick up a key and open a door. And as we can see, the mapping is indeed separating the state where we have the key and where we don't have the key, as we would expect by respecting the minimum action distance. This state representation alone is not enough to learn a goal conditional policy, because we still need to learn the mapping to the action space, to the actions. And so we propose to learn together with this state embedding also the transition dynamics. And given this transition dynamics, we are now able to move in this latent space. And we proposed a planning algorithm that roll out trajectory in the latent phase and select the first action of the trajectory that minimizes the distance to the goal state. We empirically evaluate our approach on the classic control suite from OpenAI, where we augmented it by giving a goal state, and also on two multi-goal environments where we have a grid environment and a robotic arm environment where we have to move the robotic arm to a specific XYZ position. Here we report the results for the robotic arm task, where we compare against goal condition supervised learning, a state-of-the-art algorithm to learn goal conditioned policy. And in particular, we can see that our algorithm, that is the blue line, can reach the minimum distance to the goal, while also we report the results for mountain curve 0, where here we have a different setting because we consider our planning algorithm, but we also consider to augment, to reshape the reward of a reinforcement learning agent, a DQN agent, with the minimum action distance that we learned. And as we can see by the blue line is our planning algorithm, that is the one getting the minimum negative reward. And also we have our reinforcement learning, the green line with the reshape reward, that is also getting the minimum negative reward. For the complete list of results, we remind to our paper. And thank you for listening, and hope to see you at the poster.